Okay, good afternoon, everyone. I hope you're doing great. This is the add class code. I'm gonna copy it in the chat. So would you please confirm if it works? And good afternoon. Thank you. Okay, Rachel, thank you very much. Today's content would be a convolutional part of neural networks. We technically just work on simple way of densely layered networks that the best word to describe them would be artificial neural nets. But convolutional neural nets means to have the concept of convnet, which is something new, and we are gonna go through it in the current chapter. So let's dive into it without any further delay. Let me close my can. So this is a kind of practical way of working on pictures, and how it works is imagine that in the normal convolutions in normal artificial neural nets, whenever we have a frame like 28 by 28, and if you write number 6 like that, it would totally be different from number 6, which is in the other part of the picture, or number 6, which is in the other part of the picture, right? And if you want to be able to classify all these numbers, they were all 6, but they are in different locations of the frame that we have defined, like 28 by 28. If you want to see another number 6, which in the picture is not very much centered like this, you need to have something like this among the examples that you have introduced to the neural net. So it can't classify that if there is no such example in your samples that you fed your neural nets with. So how can we tackle this problem? Look at this part. In this chapter, to solve such issues, we go towards understanding the convolutional neural networks, or ConvNet. We are going to use data augmentation to mitigate the overfitting. We are gonna use a pre-trained ConvNet to do feature extraction. For this part, the importance of this would be you don't need to start everything from the scratch. Then we are gonna learn how to do fine-tuning and visualizing the ConvNets learned and how they make classification. So Lucas said, so alignment within the frame is important, and the training set must have such cases in the training sets. That's exactly the major concept. Do we need to do feature engineering? For instance, we have to go through all 60,000 photos and center them and do all those things? That's the question, right? And do we have any solution for that? So we don't need to deal with asking everybody, okay, start scanning from the scratch, make them all centered, or just do those kind of feature extraction from the raw data sets that we have. Okay, but what is ConvNets, you may ask? The ConvNets are used in computer vision mostly because of what we exactly talked and Lucas asked. And you learn apply convets to image classification problems, and you start with something that you're very much familiar with, and that is nothing but MNIST, or that 10-digit classification problem that we already have gone through it. Look at the result that we got using normal or artificial neural nets by using just densely connected networks. Let me emphasize on this densely connected networks. It gives us 97.8%, which was great result, but can we get any further? To understand how it works, we need to see the architecture of conv2d. Whenever we want to have conv2d in our model, we need to add two things: conv2d layers and then max pooling to the layers. These are two things that we have. Look at this part. It says that let's have 32. I'm not sure what that 32 is. We are going to learn it in a few minutes from now. And then we say we have 3 by 3 window. And then this is familiar. That's the shape of 28 by 28 pixels that we have for each handwritten digit. And why we have 1 as the channel here? Anybody remembers? What is that 1? Good guess. Who else? Okay, I repeat my question. In the input shape, we have 28 by 28 and 1. What is that 1? Yes, that's the image channel, and 1 represents what? Okay, if it was 3, it showed that if it was 3, it showed that it is RGB, red, green, blue. When it is 1, it means that it is black and white, right? So this is a kind of traditional channel that we had in densely connected layers. But we are going to learn a new form of channels here. Let's see what it is. And the next part is say max pooling. What do you get from the name max pooling? What can you understand from this name when we say max pooling? It should be a group of nodes, yes. And what are we going to fetch out of those nodes? Or pixels or whatever? We are going to get the maximum number in each 2 by 2 pixels that we have. Look at this one. Imagine that we have 4 pixels here. One is 2, the other one is 107, the other one is 32, and the other one is 201. What is the maximum number among this? 201. So we are going to grab the maximum number among a 2 by 2 frame that we see here. Does that make sense? Okay, so let's go further. The next part is understanding what is happening in these layers. Look at this one in convolutional neural nets. We have conv2d max pooling, conv2d max pooling, conv2d, and then what's going to happen? It is possible to have conv2d, and one max pooling, conv2d, and one max pooling. It really depends on the architecture that you want to have in your model. But the very first thing is that's the simplest way, that you have one conv2d and one max pooling, and so on and so forth. And those numbers 3 by 3 and 2 by 2 shows the number of pixels that you're gonna have in each. So when you say 3 by 3, simply it means that you have something like this that has 3 rows, 3 columns, and it's going to have 9 separate pixels. Okay. But how we are gonna use this model, and what is the usage of all these things? What are the usages that we could consider for conv2d or max pooling and so on? And that's exactly the major part that we want to understand in assignment number 3. So most of the things that you need for assignment number 3 would be discovered in today's lecture and tomorrow's lab. Remember, we defined a model here, and that's a sequential model, and you start stacking some conv2d max pooling layers even before we get to the actual density layers, because this is going to be the beginning, and after that we are gonna connect that with the traditional densely connected layers. Okay, so guys, if you got somehow the things that we discussed so far, would you please type 2? Ivan, Lucas, thank you. Okay, that's a good percentage. Look at this one. What is the guys? Honestly, these are the parts that if you see that you feel it is complicated, because we have explained these things. I think that over 10 times I have mentioned that what is this input shape, and I cannot review the things on behalf of you. That's not the part that I can do for you. I can explain it, and if you have any question, I can go through the questions. But when we don't remember them, I can't do anything. So somebody tells, what is this 28 by 28 and 1? It's it belongs to week number 2. Anyone remembers that? Exactly. Thank you. So this part says, as our team members said, we have 28, sorry, it's not exactly 28 by 28 kind of thing. And the color channel is 1, means that it could be just black and white. So we don't have red, green, and blue kind of thing. So this is the inputs layer that we are going to have. So image height, image width, and the image channel. And in this case, we'll configure the convnet to, this is super important, to process input size of this one. But after that, we are going to generate something which has 32 channel. And that is ridiculous, because we could maximum have, we could have red, green, blue. What is that 32? What is that channel? It has nothing to do with the color anymore. Look at this one. In the MS, we'll do this by passing the argument input to the first layer. And what is going to happen after that? It says, when you get the input, which is 28 by 28 and 1 channel, the output would be 26 by 26 and 32 channel. What is that 32. Okay, we're gonna get to that. Guys, what is the relationship between 28 and 26? 28 by 28 came to 26 by 26. So we downsized the matrix by 2. A conv to D actually is going to make that 26 by 26 into 13 by 13. Look at this one. This is, if you see 26 by 26, which is 676. And this one is 13 by 13. And the division of these two shows that it's like dividing the matrix by 4. What can we get from that if we use a densely, if we use a conv to the layer, and after that we use max pooling? What is the first thing that you can get from it? You can look at this example as well. So you have 2 by 2, means you have 4 different pixels, right? And you downsize it to just 1. What is the first thing that we can achieve from that? Guys, it's not a trick question. It's just to make sure that 10% of people at least are at the computer. Guys, when we have 4 pixels here and we are going to downsize it to 1, what does it mean? Yeah, simple. We compressed the size, right? We reduced the size. This is the compression. We just use this one. And what do you expect to have when you say max pooling? Why not mean pooling? I mean, why not average pooling, like mean pooling? Why not min pooling? So as Lucas said, the reason for that with me, one of the reasons, is we tried different things and we saw that max pooling actually works the best, and that is part of the assignment. Enes, have you faced that question yet or not? Because you said that you started working on it. We are going to talk about it. No, we just go through it once. We want to compress the information. That's why if we do it 4 times for 4 different things, it's going to just multiply. So what is the use of using max pooling, right? The max pooling is going to get the maximum feature out of 4, maximum number out of 4 pixels that we have, right? We just tried 2. Okay. Imagine that, Lucas, we are not talking about 1, 2, 3 images. We talk about millions of images that we have, right? We want to have a solution that is scalable. And we are going to show in this week, maximum next week, that if we don't do the max pooling, the number of parameters, I didn't talk about this part yet. Let me just show you. Oh, we talked about this part, we didn't talk about the parameters, right? Imagine that whenever we have max pooling, we do not impose any extra weight on top of the current network. But if we do not do the max pooling, instead of 36K, we will have, after just these steps, we're going to have something like 1 million of parameters, right? So one of the things that we need to have is, yeah, we are going to see that actually just for now, just for the current moment, what we need to understand is we have something different. It's not like a color channel. we are going to use something totally different. And that channel is the number of filters. In assignment number 3, we learn how to work with a few filters. If anybody has started, you see that you're going to use some filters there. The idea is having different number of filters. As you see, we have 32, 64, 64, and they are different from each other. What is the role of those filters? I get back to the question that I started the session with. Imagine that you have a 28 by 28 pixel, and number 2 is very much neatly centered in this. This is not always the case. What if it is tilted like this and towards the top left, or it is somehow like this in the... Is it possible that I can understand what are the curves that I have, for instance, here and here? So if I can just find those two in any place, no matter if it is on top left or bottom right, if I can see those two and just those two in any picture, I could say, high probably it could be number 2, but that's not the only thing. And if I have, for instance, 1, 2, kind of 3 lines, like if you see. So if the filter, if I can create one filter that takes just the horizontal lines, like this one, so like this one, and if I have one filter that just exaggerates, using Max Pooling, remember, the just diagonal lines like what we see here. So if you have those curves, these things in any part of the picture, you can understand, it could be number 2, and it doesn't really need to have that number in the center of the picture. Do you think that you got the general idea by having those 32 pictures? If yes, please type 1. Ivan, who else? Good. Okay. Enes, imagine that, what is the, let me ask you, when we say that the number of channels in 28 times 28 and 1, or imagine that it is not 1, it is a coloring, when it is 3, what is that 3? What is the responsibility of 3? Anyone can step in and talk about this one? Even you can open your mic if you want to. So Anna said it's the channel pan depth and making it visually colored, like RGB. That's perfect. What else we can get from it? Is it possible to say it's like having 3 red, green, and blue layers, guys? Is everything super clear so far? Is it possible to say it's like having 3 dimensions? And I'm going to just make a very simple. We say the first layer red shows that we have 0 red, we have 12, we have 0, we have 32, we have 200, 2, 0, 0. We have something like that in this, and we have similar numbers. I mean, when I say similar, means between 0 to 255 for other things. Can we say each of these are gonna filter the image that we have to say this is a filter that extracts just color red, this is a filter that extracts just color green out of the picture, and this is a filter that extracts the color blue. Is it clear? So it's like you have a picture and you just focus on the colors. For instance, give me all the red components of the picture. And when you put them all together, it shows you the colory picture that you have. Makes sense, right? So what if instead of working on just colors, I work on edges. I say, okay, fetch me the parallel, give me, this is one filter that shows me the diagonal, extracts the diagonal lines. This one emphasizes on horizontal lines. This one emphasizes on the curves, for example, and lots of other filters. But because we could have many filters, 3 is not enough. Let's just pick 32. You can go for 64 or something like that. So each filter that you're going to assign is going to be responsible to fetch some features. So instead of having 3, we are going to have, we are going to have lots of filters, like 32. And each filter, when you apply it, it's this one, for instance, responsible to get the curve. So the output of this would be just these 2. This one is responsible to get the, and imagine that I'm talking about this picture, right? This is the picture that I passed. This is responsible for diagonal. So we have something like this and something small over there because we have a little bit of things over there. And this one is responsible for horizontal line. So we have this one and we have this one. And this one is responsible for the vertical line. And actually we don't have anything. So this one is going to be null because nothing is going to get out of this filter, right? So Lucas says, so instead of separate filtered frames for color, you are doing the separate filter frames for type of edges. Yes, that is pretty much what we wanted to do. Okay, guys, do you have a better understanding of continuity that number 32 right now? Okay, let's go to the next part. So we see that here we say let's have 32 channel, but one thing, imagine that I want to maximize instead of having that lengthy thing, I'm going to, in the next step, I'm going to maximize the feature. So it's like, imagine that, guys, this is something like this, not exactly, but something like this. Imagine that you use a magnifier and it's going to make this one like this. So just exaggerating the maximum features in each. It is doing something like that. When it magnifies, it reduces reduces the size as well. Yes, max pooling, exactly. So right now, if you have already started assignment, that's the very good thing, that if you have done that. Else, I strongly suggest, if you want to know the concept thoroughly, that is the best time to go through the assignment and to read these pages. And tomorrow, actually, I'm going to start doing hands-on using these examples. But let's go a little bit further before we call it a day. And we are going to have something like 1 hour of watching, over 1 hour of watching relevant videos that they help you, all of them, they help you a lot in completing your assignment. And guys, this is when I emphasize an assignment, don't think that that's like, I mean, a checklist that we have to do this. The assignment is designed to understand what is happening in Conf 2D. And the good thing about the assignment is it's going to be a knowledge that you can apply it in other places. For instance, we don't have any clear understanding of the filters that we use whenever we go to Instagram and so on, but they are exactly, they follow the same algorithms that we learn in this chapter. So if you can just learn one of them, you see that even a complex form of filters that we have in Instagram or other places, they are just combination of 2-3 of these filters that we learn in this semester. Look at the next part. It says that you can see that the output of every conv 2D and max pooling 2D layer is a 3D tensor of shape. So we had height, depth, and channel. The width and the height dimensions tend to shrink as you go deeper in the network, but the number of channel is controlled by the first. That is something that I said, so I don't know what it is, but now you see that it explains that this number is the number of channels that we are going to see it exactly in the output of, I'm sorry, we are going to see it in here as the output of that. So you said that I need to have 32 channels. And as you go, so the number of channel is controlled by the first argument passed to the conv2d layer, which could be 32, 64, and we could have 128, 256, and so on. There is no need to restrict yourself to, but the filters, it's better to use the 2 to the power of something. It makes more sense for our job. The next step is to fit the last output tensor, which is this one, into a densely connected classifier network like those you are already familiar with, a stack of dense layers. What does it mean? It means when you are done with this model in here, the last layer, after this, if you say what is the dimensions of each layer, you just simply can say model.summary and it gives you something like this. And in the last layer, which you have 3 by 3 and 64, imagine that we started with 28 by 28. It's like a pyramid that in the first we had 28 by 28 and 3, and then we imagine that we had 28 by 28, and the layer was 3, and immediately in the second layer we just had something like this 26 by 26, but the layer was not 3 like this, it was like 32. I'm sorry, I'm very bad, but you got the idea, right? It's like a pyramid that it goes, and in the next layer max pooling applies, and finally, when you get to this part, it is funny. You have something like 3 by 3, but 60. Imagine that it looks like anything but the cube. So it is like 64, and it is going to be 3 by 3, which and it is something like this. So on top of something like this, and so on and so forth, right? So let me just show you one. So if you see here, we had 3 layers, for example, and it goes like, it's like a pyramid that goes higher and higher. This is what I tried to show you, for instance, 64. And after that layer, it's the time that we call our densely connected layer. It's like we have done everything in Conv2D, and let's go to the traditional densely layer network right after that and start working on it. Okay. So the first thing that you need to do is converting this 3-dimensional layer, 3 by 3, 64, into a flattened format, which is going to be multiplication of all these numbers. So that would be the first layer. And after that, you're going to say, let's have a hidden layer of 64. And the activation value, and the last layer that we need to have, the prediction, needs softmax, because we are going to have 10 different possibilities. You know that sigmoid is not going to work. We should have something like softmax. And if you say, what is the model right now? Guys, remember, we end up having this one in the Conv2D layer. After that, when we say that flatten it, it's going to be 3 multiply 3 multiply 64, which is going to make 576. And after that, we are going to have another, that's the hidden layer, 64, and then finally this. And the funny thing is, I'm not going to take the time, but tomorrow we do it together. We'll do it together. Just look at this. Everything looks like what we had, except this is the time that we say, okay, in the model, we need to have optimizer Rams prop. The loss function should be categorical cross entropy, and the metrics that we are going to use is accuracy. And then you're going to say, okay, fit the train images and train labels. And let's have just, guys, 5 epochs. It's not crazy like 20, 30 or something. And the batch size 64. And guess what? The accuracy, just by that number of epochs, is 99.3, which is crazy compared to this number, right? So this is something that happened. We almost see the impact of it, but we don't get until this moment that what is happening behind the scene that makes it that crazy to give us that high precision. This is not something random, right? There should be a kind of mechanism. One of the things is
understand
that this is something crazy that is going to be not restricted to the global picture, but a local parameters. That is, if I want to summarize it for now. Tomorrow, we are gonna go through that together, and then we are gonna get to understand what is the actual role of convolution operator, and how it works. You see that this is a kind of, this is going to get extract from this part, and so on. We talk about these parts extensively. by doing it together. So till this moment, is there any problem, any question? If you get the idea, the general idea of what is happening, please type 3. Lucas, thank you. Arsa, Ivan. Erdo. Nati. Okay. Can you please confirm, go to the, for those who, again, wants to have the add class code. This is AHJP. And can you please go to the quiz? My suggestion is answer the quiz tomorrow evening after we finish the sections, because you're going to have better understanding to use your knowledge in the quiz. So AHJP. And can you please go to the quiz and see if it is there and you can open it? And you can open it, right? Okay, thank you very much. I appreciate your presence. I'm gonna upload the video. And tomorrow we are gonna continue our journey. Have a wonderful one and see you tomorrow.